Okay, so we have the first of today's lecture worksheets. So this is 4.1 lecture worksheets. And in this process of writing Lewis dot symbols, you will need a periodic table. So get your periodic table handy. You can use another one on the screen. I prefer my paper one that I have handy, and you will use that periodic table. Why did I write sheet? Because it is a sheet of paper. That's what I was thinking. Use a periodic table. Doesn't have to be on paper, but you will need a periodic table to find the family number. That family number is super important because it's the number of valence electrons. It's what connects all the different elements in a single column, in a single family. It's why those elements are the same, because they have the same number of valence electrons. And that number of valence electrons, what we can see from the Lewis dot symbol is it shows how many electrons are not paired up. And that will be able to predict or guide that element, that atom's reactivity. So those alkali metals with just the one valence electron, that's one unpaired electron, and that's very reactive. So very reactive, reacts with air, reacts with water, like you saw. So this is a process where you will take that periodic table family number and then put these electrons on there like they're dots. This is a stepwise process where you first pretend that you have an element symbol that's like a box. And then you will drop off those number of electrons. How many? The number of valence electrons, where you have one per side starting on the right. So let's pretend here I've got this element symbol X. There is no element on the periodic table, but let's say it's in family 8. And it has 8 valence electrons. So let's write that it's element X in family 8A, and it has, because 8A, it has 8 valence electrons. So the goal is to represent those valence electrons by this process called, the Lewis dot symbol. Now we'll see what's in the next lectures, Lewis dot structures, which represent molecules, covalent molecules. And these are very different from Lewis dot symbols. So the purpose of Lewis dot symbols is just to show the unpaired electrons on a single atom, okay? And so it's going to be different. Just remember this, when I get to that part, I say, remember Lewis dot symbols, they're not the same. They're not going to be the same, okay? So this is just an individual atom and showing its valence electrons. So I'm going to treat this element symbol as if it has 4 sides, and I'm going to put 1 electron per side, starting on the right. So I'm going to use a different color. This would be number 1. Okay, so the dot number 1 is starting on the right. The second dot is by filling up by going clockwise. So I'm moving clockwise around, it's this way around, and that would be dot number 2. So notice that dot number 2 is not next to dot number 1. Guess where dot number 3 is going? Over here, keep going clockwise around. And then number 4 is going all the way around. So to continue going all the way around, in order to drop off 8 dots, I need to keep going around to now start pairing up. So this is number 5. And then continuing around, this is number 6 next to number 2. This is number 7. And then this is number 8. So they paired up after filling all the 4 sides. So 1, 2, 3, and 4, and then starting around the second time was 5, 6, 7, and 8. So there's a maximum of 8 valence electrons. You can't put 10, but you can have less than the maximum. So you can have less than 8, and that would be because of the family number. Let's say you only had 5 valence electrons because it was in family 5A, and that will then result in some electrons being not paired up or unpaired electrons. So we'll see that in these examples down below here. So first you need the periodic table to look up sodium. So sodium is the element symbol Na. Find it on your periodic table. You should find it in family 1A. And so family 1A, that number 1 means there's 1 valence electron. And so the Lewis dot symbol, you start by writing the element symbol, and then you need to put 1 dot. That 1 dot is going to go on the right side right there, and that's it. Don't need to do anything else because there's only one. Continuing to aluminum. So aluminum, you need the element symbol for aluminum, which is Al. Then you need to find aluminum Al on the periodic table. So look for it, and you should find it in family 3A. That number 3 means that there are 3 valence electrons. And so you want to start by writing the element symbol Al and then putting dots on there. Starting on the right side, you have 1 and then 2 and 3 moving around. So those are 3 electrons, not paired up, all unpaired electrons. And so when you have an unpaired electron, these are very reactive. And so what happens is these will be lost. And we can lose this one electron to form the sodium +1 ion. And that's what happens in the formation of an ion. So remember, family 1A forms +1 ions. Well, aluminum has 3 unpaired electrons. And guess what happens to those 3 unpaired electrons? This will lose those 3 electrons to form everything in family 3A forms a +3 ion. So aluminum 3+. And so that +3 is less 3 electrons, and that's why it's +3, because you still have the original number of protons in the nucleus. So this is, the next one is carbon, which is the element symbol C, and you will find carbon in family 4A. So there are 4 valence electrons, and then the Lewis dot symbol, you start with the element symbol and you want to drop off 4 electrons. So starting on the right side, 1, 2, 3, and 4. Now carbon is interesting. Carbon is a non-metal. It's to the right side of the stair-step line. And non-metals can have some options. Non-metals tend to form covalent compounds. Remember, a covalent compound is 2 or more non-metals. But carbon is also in the position where it can act as a non-metal in an ionic compound. So in that process, carbon can actually gain or lose electrons. And this would be all 4 electrons. And this can form, most commonly, it will form the anion C4 minus. As a non-metal, it tends to pick up electrons, gain electrons, and form the negative ion. But it also can gain electrons by sharing, and that's forming a sharing electrons, which is a covalent bond. And we'll get back into exactly what goes on in the process of forming bonds, but it starts with understanding that there are electrons that are valence electrons, that's on the outside of the atom, and those valence electrons are what are lost and gained in forming an ionic bond or a covalent bond. And so the number of valence electrons is important in why this atom will be more reactive, because there's only 1 electron it has to lose, or a little less reactive because there's 3. You have to find 2 more compared to the 1 to lose your electrons to. Okay, this is nitrogen, the next one. So nitrogen is the element symbol N, and you want to look at your periodic table and find that it is in family 5A. So if there are 5 valence electrons from that family number, you want to start with the element symbol N and then drop off 1, 2, 3, 4, and then the 5th one will pair up. So this has 1 pair and then 3 unpaired electrons. And so what will happen is that this is similar to aluminum, where aluminum can lose 3 electrons. This can gain 3 electrons and to form the nitrogen anion, which is N3 minus. And so remember, everything in family 5A forms -3 ions, just like everything in family 3A forms +3 ions. When you lose electrons, losing electrons, this forms a cation. That's the positive charge. But when you gain electrons, this forms the negative charge anion. Okay, that's because picking up electrons adds more negative charges to the atom, and losing electrons loses negative charges, but you still have the original number of protons in there. So there's going to be an overall positive, more positives than negatives when you lose those electrons. So let's take a look at this next one. So xenon, which is the element symbol Xe, that's you'll find in family 8A. It's not element X, that was a made up element, but Xe is very similar to the X example. It has 8 valence electrons. So you would write the element symbol and then drop off 1, 2, 3, 4, 5, 6, 7, and 8 electrons. So there are no unpaired electrons. And so this is why this is not reactive. And this is why all of the elements in family 8A, these are called the noble gases, all of them are not reactive because they don't have any unpaired electrons. They don't want to lose electrons. There's no need to gain electrons. These are all filled up. Basically, all the sides are filled. Okay, so it is completely filled with electrons. It doesn't need any more electrons. And so that's why it doesn't react. This is electrons losing, gaining, sharing electrons. This is why atoms will react with each other in order to exchange, share, or share those valence electrons. So this last one is hydrogen, which is the element symbol H. And there's the hydrogen you will find in family 1A. This means it has 1 valence electron, and you can draw it like this with 1 dot. Now, hydrogen and helium, they both are unique on the periodic table. They need only 2 electrons to be filled. Just like xenon, this example of xenon is filled and it's not reactive. Okay, so the valence electrons having 8, having all 4 sides filled with 2 is 8. So 8 valence electrons is filled and stable. Well, to be filled, you only need 2 electrons, and to be filled means to be stable. And so what happens is that hydrogen only needs to lose 1 electron. So losing 1 electron will form this hydrogen plus 1 ion, okay? But the thing that's interesting about hydrogen is hydrogen can also act like an element in family 7A and also can gain 1 valence electron to form this other ion. And we looked at both of these versions in the monoatomic cations, where H plus is the hydrogen ion. It has a +1 charge. That's a positive charge cation. H minus is the hydride ion, and that's the negative charge anion. Now notice, even though family 7A should have 7 valence electrons, hydrogen can't have 7 valence electrons. Why? Because it only has 1 electron. It has 1 electron, but because it can gain 1 electron, that's similar to all of the elements in family 7A. Those elements in family 7A, those are called the halogens. They all also gain 1 electron. And so they will be forming the ions like F minus, Cl minus, Br minus. If you look back on your monoatomic cation, that cheat sheet, you'll see that those all in 7A form -1 charge anions. And so because hydrogen can do the same thing, it can act like those elements in family 7A. That's why hydrogen is also listed in family 7A, because it acts like the same, even though it doesn't actually have 7 valence electrons. And so helium is something that is also only needing 2 electrons to be filled. So helium, the Lewis dot symbol, with its 2 valence electrons, the way that the Lewis dot symbol looks for helium is not going to be like this, He with 1 and 2. Because if you draw it like that, it means they're 2 unpaired electrons, which means they're unstable. Instead, you write it like this, helium with the electrons paired up. So the electrons are paired. Hold on a second. Let me write the word before I answer your question. Yes.
Oh, I was just going to say, we can't see what you're writing because the screen is like being cut off. I think you have to, thank you.
Okay.
Now I can see what you're writing.
Okay.
Sorry.
That's okay. Thanks for letting me know, because the bottom of my screen looks okay, but there's, as long as it's not, you're not telling me like I forgot to record, then I would be like, oh. Okay, so the electrons are paired up, and this is because there's only 2 electrons, and having only 2 electrons means you don't want to write them as they're unpaired. Helium is special. It is, those 2 electrons are filled and basically filling this up, and it is stable just like this xenon. Okay, so just like this is paired, and so this is stable. And so helium acts like everything else that is in family 8A. That all of those elements in family 8A are stable. They don't want any more electrons. Xenon is not reactive. It has a filled valence shell with 8 electrons. Helium also has a filled valence shell. And so that's why you find helium in family 8A all the way over on the right. It doesn't have 8 valence electrons. It only has 2. But why it is in family 8A is because it acts like all those other elements in that family. Because it is filled with the 2 instead of needing 8. Okay, let's record this. The sodium atom has 1 valence electron. It's not stable. The sodium ion lost that 1 valence electron. Remember, this is loses 1 valence electron. And in that process becomes this stable sodium ion. So that's Na+. And that is what is out there in the universe. You don't actually have sodium because it's already reacted and formed this stable ion, which has already lost that 1 electron. The same is true about aluminum. So aluminum is rare to find as individual atoms. Now, again, you can't see these individual atoms, but if you have a sample of aluminum, more commonly it's already as the aluminum ion that has already lost those 3 electrons, and it's aluminum plus 3 ion, which is stable. So the ion is stable because they obey that octet rule. And so that is something where, getting back to the carbon can gain those electrons and form that ion, C4-. It can also share electrons to form a covalent bond. Why does carbon want to do that? What drives the formation of the bond is carbon wanting to pair up those 4 unpaired electrons to obey the octet rule. So to obey the octet rule is the whole goal of what atoms have. Just that, you know, the thing about atoms and the universe is that there's no brain, there's no processing unit for each individual atom, but atoms are driven to form bonds. And this is not driven by a brain, it's driven by this, which is called the octet rule. And this is to have a filled valence shell and to have no unpaired electrons. To fill that outermost energy level, which is called the valence shell, and have it with 8 valence electrons. That's why it's called octet. So you're going to either have 8 valence electrons or 2. And when would you have 2 valence electrons is when you have hydrogen and helium. Okay, but the majority of the periodic table, and those are all the elements in the A series, have those the octet rule, and they want to have 8 valence electrons. And so everything on the periodic table, if you look at your periodic table, you've got all these elements on there in these columns. So everything in families 1 through 7 are not really stable, and you're not going to find lithium atoms. You're going to find lithium ions. You're not going to find oxygen atoms. You're going to find oxygen as the ion. And so this is most of the periodic table is not obeying the octet rule. All those elements with those element numbers, the family numbers, are not 8. They're 1, 2, 3, 4, 5, 6, 7. And that's not obeying the octet rule. So elements will lose electrons. Those are metals. I'm going to write it on here. Metals tend to lose electrons because they can lose electrons to get to 8, going down to 0. And nonmetals on the right side tend to gain electrons. And this is gaining electrons and losing electrons. One metal will lose an electron to a different nonmetal. And then those are ions that then form the ionic bond. So we're going to get to that looking at those bonds in formation of, or we looked at the formation of those bonds, and that's why we got into, before the looking at this process of the valence electrons, we looked at writing the chemical names, and when those ions form, you use the crossover rule. So this is why the crossover rule happens, is that atoms have valence electrons, they're not stable. So they form ions, and then those ions bond together. And so that's the formation of ionic compounds. So if you already got to take notes on this worksheet, great. This is just reviewing it again, that the carbon cycle is a natural process in our Earth's atmosphere and also on Earth. It's all the carbon that's moving through. Some of it is as the gas carbon dioxide that you've heard of. So, but it's not all of it. So there's carbon in all different compounds on Earth. Some of it is buried underground, like carbonate minerals in rocks. That's really coal. And fossil fuels, that's oil and natural gas. So oil is also called petroleum. And also natural gas is a fossil fuel that is buried deep underground. So these 3 fuels, coal, oil, natural gas, they're all deep underground. And they're deep underground because of this, this basic thing that happened 65 million years ago. It's believed that Earth was hit by a giant meteor, asteroid, and killed off everything at once. And all of that became buried, and it was once living. So all the plants, all the animals, not just dinosaurs, everything that was once living, which was made out of carbon, was then buried for millions of years, and over time formed bonds that became this stuff that's buried underground: the coal, the oil, and the natural gas, which are these underground sources, were basically meant to be underground. Humans started digging these things up in the industrial era about 200 years ago, to use the coal, to use the oil, to use the natural gas. Now, there have been some benefits from this development, basically, but there's always a downside. Or not always, but there's a downside to this. So this is the, here, these are underground sources are in black. So the underground sources are in black, and then the carbon that is moving through the system, that's in red. So let me move this here, moving back up, is that you have carbon moving through the system. Some of it is meant to be underground, and is artificially being brought up underground. And that's what we'll look at, is shown in this worksheet. And then some of it's natural. But this carbon is bonded to other atoms in carbon dioxide. That's one compound that's moving through the system. And the majority that is focused on here is carbon dioxide gas in the atmosphere. So that's atmospheric carbon dioxide. But we also know that carbon is a gas in this carbon monoxide. We talked about that in the air pollutants. And then we also know that there are, this is methane gas. So that's CH4. Remember, that's called methane. So all those compounds that are stored underground, the fossil fuels, well, those are a lot more bonds between carbons. So this is an example of what's called a hydrocarbon. We talked about hydrocarbons in covalent compounds, but hydrocarbon compounds have only carbon and hydrogen, and they are generally in fossil fuels. And it is a fossil fuel that uses the hydrocarbon to burn in a combustion reaction. We're going to focus a lot on combustion reactions coming up in lab. But if you've ever burned a piece of paper or burned wood or driven in a car that's burning gasoline or flown in an airplane that's burning jet fuel, those are all hydrocarbons. Those are all fossil fuels that have been dug up or pumped up from underground and are being used in the combustion reaction, which is burning. And the process of burning releases heat. You know that from fire if you've burned paper or wood, but it also releases energy that can be used. And that's the energy that powers the engine of the car or the engine of the airplane, or just heating when you burn the wood or the paper. And so fossil fuels are useful in that way, but there's a downside to that. The burning of fossil fuels has led to atmospheric carbon dioxide levels increasing through the decades since the beginning of the industrial era. So there's carbon in the system. Some of it is moving through the system and some of it is underground. And basically underground is not necessarily meant to be moving through the system, but we are moving it through the system. So let's circle the compounds that are moving through the system. Everything that's moving through the system, we can circle in red. That is red. Okay, so what's moving through the system? All of this atmospheric carbon dioxide, this is moving through the system. Okay, and so the compounds that are stored in reservoirs, that's what's shown in black. And so that's sand and silt. That's carbonate minerals in rocks. That's that coal. That's all underground. It's stored in a reservoir. And it's literally underground and in the bottom, okay? But it's also in black, so that helps. The fossil fuels, that's the oil, petroleum, natural gas, that's all stored and meant to be. There's also stuff at the surface. So at the surface, we have forest. So that's wood that is in trees. That's stored. So those are reservoirs, and soils also have carbon compounds, and that's also stored. And surface water and deep ocean also has carbon in it, and compounds in the surface water and compounds in the ocean that have carbon atoms as part of those compounds. So those are all meant to be stored compared to atmospheric carbon dioxide that's moving through. So what are the two largest reservoirs that I just circled in black? What are the largest number values for those blacks, the reservoirs? So looking for the largest number values, take a look at all of those. Let's see, they're all pretty large. So this is 1.2 times 10. I have to erase this because I wrote over that. Okay, so this is one of them, 1.2 times 10 to the third gigatons, which is less than this one, 1.8 times 10 to the 7 gigatons, which is less than this one. This is the biggest number. This is 2.5 times 10 to the 7. This is G, which stands for giga. So that's gigatons, GT. And so that's the largest reservoir, and that's fossil fuels. That's the biggest number, right? The second biggest number, just checking all of them, so because I kind of obscured this. So those are all 10 to the third, and that's 10 to the fourth. So the second biggest number is also this one. This is 1.8 times 10 to the 7 GT, which are carbonate minerals in rocks. Remember, what's that? That's generally going to be coal. So we're digging up all that. We're pumping up fossil fuels. We're digging up coal. Those are reservoirs that are meant to be stored, but we do use them. And so the compounds in the reservoirs, they are meant to be stored. There's a lot of it, right? But we are actually moving it through the system. So they're unnaturally being moved through the system by being burned as fossil fuels and coal. And we'll see that this is burning mostly to generate electricity, but also transportation. Now you might say to yourself, I don't burn any coal. I don't burn any oil. I don't burn any petroleum. You actually do every time you're using electricity. Right now, all of us sitting on Zoom, sitting at our computers. If you're charging your phone, you're using electricity, which means coal is being burned somewhere. Oil is being burned somewhere. Natural gas is being burned somewhere in order to generate that electricity. So we'll get to that in module 6, exactly where our electricity comes from. And we are literally burning those fossil fuels every time you're using electricity. There's also transportation. That's a clear link whenever you are using a car or an airplane or a bus. That transportation source is burning a fuel, gasoline, jet fuel, diesel fuel. And that is a clear burning reaction. It's a combustion reaction similar to basically burning coal to generate electricity. And so those are unnatural. This process of burning fossil fuels did not always exist. Humans have been around for a long time and only discovered the coal and oil and petroleum within the last 200 years. So the processes that add carbon atoms in the form of carbon dioxide to the atmosphere, we're going to use a plus sign. Okay, so let me see. The processes that add, that's actually the arrows that are coming out. So this arrow coming out, respiration adds, so that's a plus sign. And so what respiration is basically the exhaling process. So respiration, exhaling, humans exhaling, but plants also do it in their night reactions. And this is also, we get from the ocean, this arrow coming out. This is adding carbon dioxide from the ocean. And that is also the bacteria, microbes in the ocean also respire. They also exhale and release carbon dioxide. And then this is here, deforestation. This is an arrow coming out. So that's adding carbon dioxide to the atmosphere every time trees are cut down. Why are trees cut down? To clear the land for farming or to use the trees, let's say for wood and paper. And this is partly where humans come in. And then finally, this arrow is the fourth, the last one of adding, and this is adding by burning fossil fuels. Now, let's take a look, though, at the processes that remove carbon atoms from the atmosphere. And some of these are natural, so using a negative sign for that. I'm actually going to switch to the green for the negative sign. So this is the arrow coming out. So how does carbon dioxide get removed? By reforestation. What's reforestation? This is planting trees. So this is a process that is naturally matched. So deforestation naturally matches reforestation. There is one part of it that is a little bit, the numbers are mostly equal, 1.5 versus 0.5. So this is 1.5 gigatons per year versus 0.5 gigatons per year. That if humans weren't around, plants, trees are removed from nature. They die, they're natural fires, and they regrow. But humans are involved in this process of deforestation that is not matched. So deforestation is one of them. Humans cut down more trees than can be replanted or regrown naturally. That's not as big as, the other process, which is burning fossil fuels. Okay, so I'll get back to that, but I want to get to the processes that are matched. So deforestation and reforestation are matched. Interestingly, photosynthesis and respiration are also matched. Photosynthesis takes carbon dioxide out of the atmosphere. I actually was going to do that in green, so I'm going to do that in green. So carbon dioxide out of the atmosphere. from photosynthesis. So this is taking it out. Well, this is also a process that is naturally matched. So respiration is naturally matched against photosynthesis. And looking at the numbers, you can see those numbers are pretty close. This is 60 gigatons compared to 61 gigatons. And so that's basically plants doing their thing. They release carbon dioxide in their daytime reactions, and then they take in carbon dioxide, they take in carbon dioxide through photosynthesis in their daytime reactions when exposed to sun, but then they release carbon dioxide in their nighttime reactions, and that's respiration. So that's a natural process, and that's naturally matched. Another natural process that's naturally matched is this one. From the ocean puts in carbon dioxide, but the ocean also takes back in the carbon dioxide. And it's similar to what plants do. Bacteria, microbes in the ocean also take in and exhale carbon dioxide. So from the ocean and to the ocean are roughly equal. And so that number is 90 gigatons compared to 92 gigatons. So that's a natural match process. That's a naturally matched process. This one does not have any match, and I'm going to circle it in red. And this is what humans do. Humans came along and started burning fossil fuels to the tune of 6 gigatons per year, you can see on here. And that is not part of the carbon cycle. So this is the one that is most influenced. It is not part of the natural carbon cycle. It is not matched. And that's where I was in the video mentioning that in the basically evolution of Earth, Earth kind of set these balanced processes: deforestation, reforestation, respiration, and photosynthesis. This is all balanced. Well, when humans came along and started burning a lot of fossil fuels in a short amount of time, there's no natural balance for this. Now, maybe if you give it another 100,000 or million years, something will evolve to take in fossil or carbon dioxide because Earth will survive. But we have upset this balance of the natural carbon cycle by coming along and putting in a bunch of carbon dioxide in a short amount of time. Okay, sheets. Okay, so back to the worksheets. We're on to the last one, which are just some of the graphs that were shown to the world from atmospheric scientists, first showing the carbon dioxide levels increasing. And this was not really accepted. It took some time, unlike the story that we had last week, which was the ozone hole. Remember the graph that showed chlorine from chlorofluorocarbons in the South Pole over Antarctica, that chlorine amount caused ozone decomposition. So that graph was completely believed, and within 15 years, they banned chlorofluorocarbons all around the world with the Montreal Protocol. Well, what we had with carbon dioxide is atmospheric scientists saying carbon dioxide levels are increasing. Carbon dioxide levels are increasing. Look at this graph, look at this graph. And we're going to look at these graphs. But there was some disbelief, not the same. It was not accepted in the same way. And there are many theories as to why, but one, which we can definitely throw out one, which is, hey, we can't see any of this. Well, come on, we couldn't see the chlorine free radicals either. But one is that it was linked to industry. It's linked to the world. The world makes money off of transportation and making things, and electricity is needed to make things. And so it is political, not just science. So that's an issue. But looking at the graphs, so here's the data. And so we're going to get through this kind of chronologically. This is one of the very early graphs showing increasing carbon dioxide concentrations. And I showed you this in the video, but we're actually looking at this because one goal I have in Chem 9 for you is to understand, looking at a table, like when we looked at the air pollutants and the standards for the Environmental Protection Agency. Looking at a table of data can tell you a lot of information. And a graph can also tell you a lot of information, but you have to understand what you're looking at. So ability to understand those graphs, it's not just important in chemistry, but often you are given information like financial information as a graph. And so you want to know what that information is telling you, which is, sell your stocks or start saving more money or start spending some money because you're saving enough. And so graphs are starting with looking at the x-axis. So that's the horizontal axis. And then you'll also hear me talk about this a lot, the y-axis, that's the vertical. So on the x-axis here are years. And so the years go from 1960 to 2010, okay? And then on the y-axis, this is what is reported, the carbon dioxide concentration in the units of parts per million. So the units for this data are years on the x-axis, and also the units on the y-axis, which they're showing us the data for, are ppm, parts per million. So remember that parts per million, we talked about that with air pollutants, and you'll see it again, but that is how many parts in a mixture. And so the parts are of carbon dioxide. So this is carbon dioxide concentration, carbon dioxide that is in the atmosphere, or atmospheric carbon dioxide, the same atmospheric carbon dioxide that we looked at in the carbon cycle figure in the last worksheet. Okay, so we're looking at how much carbon dioxide is in the atmosphere, and we can see that the concentration in 1972. So for looking for the concentration in 1972, you look at the year on the x-axis, find 1972, which is going to be between 1970 and 1980. Well, I'm going to put it about here. Okay, and so then this is going to come up to here and find that over on the y-axis will tell me that it's somewhere between 320 and 340, maybe a little closer to 320. So let's say about 325, and then the units ppm. How about the concentration by 2002? So again, you got to go to the year on the x-axis and closer to 2000 than 2010. So I'm going to go to about here, skipping over that inset graph, and then come on over and see that it's between 360 and 380, kind of in the middle, so about 370 parts per million. So the inset graph indicates the carbon dioxide in just a single year. And that basically is blowing up just one of these. So in 1 year, you have an up and a down. In 1 year, you have an up and a down. Okay. And so that's because of how the Earth basically faces the sun, and the northern hemisphere versus the southern hemisphere. The northern hemisphere versus the southern hemisphere, there's more of a release compared to absorbing carbon dioxide, because the southern hemisphere actually has the Amazon rainforest that absorbs a lot of carbon dioxide when it is facing the sun during our summer months or their winter months. So we've got this in a single year goes up and down, but overall you can trace this overall upward increase of or in atmospheric carbon dioxide. It went from somewhere around the 300s to close to 400 on this graph. Okay, and so where we are now is over 400 parts per million carbon dioxide. And that's this next graph. So skeptics said that just goes to 1960. We don't know what the carbon dioxide concentrations were before 1960. And so that's what was involved with the ice core data, because in order to go back in time, you'd have to go back in time. And that's not possible. But that's the interesting thing about the ice core data, is there are snapshots of time you can take by drilling down into a glacier that's been around for 10,000 years or 100,000 years, or even 800,000 years are some of the oldest glaciers on Earth. So when you drill down, you actually get a little snapshot of what the air was back then. And you can sample that air and measure a few things. You can measure the atmospheric carbon dioxide directly. You can also measure the ratio of carbon isotopes, which will then trace where the carbon dioxide came from, if it came from fossil fuel sources or burning fossil fuel. And then you can also measure the water vapor in the air bubbles, and you can measure the ratio of the hydrogen isotopes. That's why we talked about isotopes. You can measure the ratio of the hydrogen isotopes in the water vapor in those air bubbles so that you can get basically a measurement or a hint, an idea of what the temperatures were by measuring those hydrogen isotopes. And so that, though, getting back to the carbon dioxide concentration, this was just one of the measurements you can take, is the actual measurement of carbon dioxide gas in parts per million. So it's still carbon dioxide concentration in parts per million. But it goes further back. It goes further back in time. And how were they able to go further back in time? Using the ice core data. So this is an ice core in Antarctica. So all of the current data was just taken air samples over Hawaii. Well, when you go back in time, you have to go into these ice cores. Okay. So drilling down to go 1,000 years back, 1,600 years back. And this is basically the year is the year 1000 compared to the year 2000. So this goes back to 1000 AD compared to where we are now, which is 2021. Okay. So what was the concentration back in 1800? So 1800 here on the year, the x-axis, this is about between 250 and 300. So let's say about 270 parts per million. And then you've got compared to 1300. So looking at 1300 on the x-axis, we don't have 1300. So I'm going to mark it here and then move up and see that it was still about 270 parts per million. So this has all happened, that carbon dioxide concentrations were stable. On this graph, they were stable. They were about 270 parts per million before 1800. Okay, so before the year 1800. And why is 1800 important? Because that's the beginning of the industrial era. So the industrial age in history is when humans started digging up coal and using it and burning it for heat, but burning it to use in steam locomotion engines or steam powered factories. When you burn carbon, or when you burn coal, when you burn oil, you can use that fire to make steam, and that steam can move a generator to generate electricity, or it can move an engine, and that's how you have a steam locomotive engine. So that's what happened in the industrial era. We started burning a lot of fossil fuels. And so the burning of fossil fuels, we already saw, has an effect on the carbon cycle. It's putting carbon dioxide in the atmosphere that was not necessarily meant to be put in the atmosphere and does not have a natural removal process. Okay, so this gets us to, skeptics said, that goes 1,000 years back. We don't know what was happening more than that. Maybe it's just a fluctuation. And it's true that Earth has fluctuated in the amounts of carbon dioxide because of ice ages. We know there's proof that the Earth has been warmer, the Earth has been colder, there's been more carbon dioxide, there's been less carbon dioxide because of volcanism or volcanic eruptions. Carbon dioxide temperatures have varied throughout the years. And so that's what this next graph is all about. Scientists said, fine, we'll dig further down and we'll get more data. And so more data is this graph. So on the x-axis, this is present day is year 0. And then this is going back in time. Going back in time on this graph goes to about 400,000 years ago. So this is meaning drilling further and further down gets you further back in time. And this actually has a graph that goes back 800,000 years. But the information that's presented in this graph is a little more complicated. This shows temperature in addition to carbon dioxide concentrations. So we have the temperature in red and the carbon dioxide concentrations in blue. And that's why this graph looks a little more complicated. You've got red overlaid with blue. But what you can see that over time, from between 0 and 400,000 years ago, the temperature has gone down, it's gone up, it's gone down, it's gone up. That's the blue. So the temperature has its cycles, and that's the overall climate. So let's not call it climate, let's call it Earth's climate is the overall temperature. So I'm actually crossing out temperature, but it's temperature that is measured. So climate has changed. It's gone down, it's gone up, but relative today, it's been within a window. It's been within this window of between 5 and -15 degrees, -15 and +5 degrees Fahrenheit over 400,000 years. And we also have data showing that the temperatures, the climate has cycled in the same way for 800,000 years before present time. And this is also true about the red. So the red, oops, don't want that in red. I want just this in red. The red line is, sorry, the red line was temperature. So temperature has cycled, and also carbon dioxide concentrations, that was in blue, that has also cycled. And so that's gone down and up and down and up. And it has been between a range of this side, about 200 to 320, between 200 and 350, let's say, parts per million over 400,000 years. And again, they have this cycles are shown going 800,000 years ago. So what's the problem? The problem is this part, which I will put in purple. Well, now we're at over 400 parts per million of carbon dioxide. And what will happen to the temperature? If the carbon dioxide goes up, well, carbon dioxide is a greenhouse gas. We know that temperatures will go up too. We know they will go up. The question is how much? How much are temperatures going to go up? Okay, and so, whoops. How much are temperatures going to go up? We know that this is way above the carbon dioxide concentrations that have ever been in the last 800,000 years. And so what are the temperatures going to be? And so that is something where it's historic. Humans caused this, and we are gonna have to get ourselves out of this. So I want to show you this simulation of climate change. Next, let me switch over. Okay, so we know climate change has data backing it. Well, you guys know now. So climate change is based on data. We have carbon dioxide is in the atmosphere and you can't see it. We can't see that carbon dioxide, but we know it's there and we are putting it there. We know how it got there, and we know that it is rising. The amount of carbon dioxide in the atmosphere is rising, has been rising. And we also know that carbon dioxide in the atmosphere causes temperatures to rise because it is a greenhouse gas. Now, exactly why carbon dioxide is a greenhouse gas, we will get to in the molecule shape. Okay, so the molecule shapes we'll look at, but it is something you can't see. We can't see the carbon dioxide, we can't see the shapes, but we know from the chemistry. We can measure the carbon dioxide, and we know that we can look at the molecule, which we'll get to, and see exactly how carbon dioxide traps heat. It doesn't trap heat with like a trap where you trap an animal, it traps heat in the molecule. And so, but let's go back to, this is a graph shown here that is the one that I've been referring to, that we have carbon dioxide information and we have temperature information. So first, let's look at the carbon dioxide information. So, and remove the temperature. So here we are, this is year 0 on the x-axis, and on the y-axis is parts per million of carbon dioxide. So this is a turquoise line, and you can see that the amount of carbon dioxide right now is above 400 parts per million. This graph, though, for 800,000 years on Earth, the amount of carbon dioxide cycled from somewhere between 180 to about 300 parts per million carbon dioxide. Why did it cycle? Why did it go down and up and down and up and down and up and down and up? That's the ice ages linked to, which are linked to, you can link this to fluctuations in Earth's orbit. A little bit of wobble leads to ice ages, and those can be predicted, but they happen over not 10 years or 100 years. So you don't need to start worrying about the next ice age coming on or Earth being wobbly. It happens over 100,000 years. So this change, carbon dioxide, happened over 100,000 years. In 100,000 years, that allows for organisms to evolve and adapt to the changing amount of carbon dioxide, or more specifically, what changes with carbon dioxide is the temperature. So this overlays the temperature onto the carbon dioxide concentrations, and they're linked. So temperatures go down and up and down and up and down and up with the carbon dioxide concentrations. Why? Because carbon dioxide traps heat in Earth's atmosphere. And so the temperatures are what organisms have to evolve with. They have got to adjust to the temperatures. The carbon dioxide, it's less than 1% in the air. That doesn't do anything. You're not going to have like need more oxygen or be breathing more carbon dioxide. It's minimal. The effect is the temperatures when carbon dioxide changes. And let's talk about it in a bigger sense. It's the climate. And so the overall, over 100,000 years, animals could adapt, plants could adapt for increased temperatures or decreased temperatures. And though you do have die-offs in the ice ages, you do have overall living things can adapt and stay living. Well, here's the question. What's going to happen to the temperatures with the carbon dioxide increase? Well, we don't know, but they're expecting to go up. We just don't know how much. And then can animals, can organisms, can humans, can plants adapt to these rising temperatures? Well, we don't know. And so that's what we're getting at with climate change and climate mitigation, which it's happening now. We see the changes, we see the results, but we also see people changing and governments changing and industry responding. It has to be just like the response, if not better, than what happened when the link was made between chlorofluorocarbons and the ozone layer. We all share this problem of carbon dioxide. We all produce carbon dioxide. You're producing it right now. I'm producing it right now. Our electricity use is producing it, our transportation, but we all can change this. We all have to change it because we all share this carbon dioxide, just like we all share Earth's atmosphere and we all share that ozone layer. So that's what I have.